Yeah, so I did want to go very briefly over, so yeah, Kareem, you told me that you solved number 4, number 5, and number 8, but I'd like to go over them very quickly. So let's start with number 4. Um, uh, Kareem is here as well. Okay, good. So, sorry, my iPad is lagging today. Um, Great. So we're going over number 4 from the homework. And so this problem is to, let's see, so let P, so P is prime. And I realize for this stroke, we need to be P is a prime greater than 2. Otherwise, this doesn't work. And the problem is the following. So you take 1 over 1 plus 1 over 2 plus 1 over 3 all the way to 1 over P minus 1. And we write this as R over S, where these are no common factor. So we write the fraction in lowest terms. And the problem is to prove that P divides R. Okay. And now I will make a comment here, which is, so I'll make maybe some comment, which is, why did I include this as modular arithmetic? Because, yeah, I guess the point is what? It's equivalent to showing that 1 inverse plus 2 inverse plus all the way to P minus 1 inverse is congruent to 0 mod P. And so by inverse, what do I mean? I mean multiplicative inverse modulo P. Okay. So that's what I mean. And yeah, and so maybe I'll make it so it was important that all of these denominators 1, 2, 3, P minus 1, none of them are divisible by P. In fact, they're all co-prime to P, right? And so because of that, it's equivalent, proving the problem is equivalent to showing that the sum of the inverses is 0 mod P. Okay. And maybe I can just give a proof of why that's true. So the point is, if you look at 1 over K versus K inverse, so yeah, so let's think of um, so K inverse, what is K inverse? So K inverse is represented by some integer so that P divides K times K inverse minus 1, right? So you can think of it as K inverse as an integer where this is true. And then the point is if I do 1 over K minus K inverse, this is equal to, maybe I could do it the other way, K inverse minus 1 over K. This is K times K inverse minus 1 over K. So this is a fraction. So this number where P divides the numerator and not the denominator. Does this make sense what I'm saying? So I'm not saying it's a reduced fraction. It might not be reduced, but it's a fraction where P divides the numerator and not the denominator. And so in particular, if I take let's say I take 1 inverse plus all the way to P minus 1 inverse, and I compare this with 1 over 1 plus 1 over 2 plus 1 over k minus 1, or p minus 1, this is also going to be a fraction. Let's say it's a over b, right? Then p divides a, and p does not divide b. Okay, and so then it follows, right? Because you know, if this were some integer divisible by p, and this is some fraction where p divides the numerator, then this is also going to be some fraction where p divides the numerator. Does this make sense, what I'm saying so far? So,
Yeah.
yeah. So I bring this up because if you haven't seen it, it's very, I don't know. Maybe it's kind of unintuitive to think about fractions as like residues modulo p, but you can really do this. Yeah. Abdullah, did you have a comment, sir? I think I might have cut you off.
I was just saying, yeah, it makes sense.
Okay, good. Okay, so yeah, so it's equivalent to just doing, showing this thing about the residues and their multiplicative inverses, but this one maybe is not um, that hard. Maybe someone can give me some idea why this is true.
Because equals to 1 plus 2 plus b minus 1.
That's right. That's
Or
right.
it's
So
congruent to, yeah.
that's right. Yeah. So yeah, maybe we'll just maybe I can duplicate this. Yeah. So it's just yeah. So let's say we've proved it now. That's right. So Karam is saying that this sum, 1 inverse plus 2 inverse plus all the way plus p minus 1 inverse, is actually equal to just 1 plus 2 plus all the way to p minus 1 mod p. And of course, why? Because the set 1 inverse, 2 inverse, if we just take the set of residues is the same as 1, 2, in some order, maybe in a different order. Just, yeah, so the set of the inverses of the residues is the same as just the set 1, 2, all the way p minus 1, in some alternate order. And yeah, so of course, what is the proof? Well, the proof is, well, okay, if x is not congruent to y mod p, then x inverse is not congruent to y inverse. Okay, so they're all different. Okay, they are all different, and there are p minus 1 of them. Okay, so it's a bijection. Yeah. Does it make sense? I didn't write too many details, but hopefully it's clear why it's true. Did it make sense why this claim is true?
Yeah.
Okay, good. So yeah, so then I guess we're done, right? So then this guy is equal to what? This is congruent to well, okay. Uh Maybe we should be a little bit careful. This is p times p minus 1 over 2 which is equal to, so now this is why we need p needs to be odd, right? Because this is going to be p times p minus 1 over 2, which is 0. But you need p to be odd, right? Otherwise this doesn't really make sense. Yeah. So maybe I'll make need p odd for this last step. Okay. So maybe I'll ask a question now. Is it still true if p is not prime, right? Like, does this in this argument, where did we use that P is prime?
That every number under less than P has an inverse.
Oh, okay, very good. Right. What if we only summed over the numbers that are coprime? So what if we did something like, yeah, so instead we say, okay, maybe P is not prime, P is just some number, and we did sum over A such that, so A is between 1 and n minus 1, and A is coprime to n, and we did sum of 1 over A is equal to R over S. So now, is it true? Or maybe I don't know if it's true, but can you prove, or yeah, can it be? I don't know. Maybe I'll say, is it true? That n divides R. Um, and so again, I think the condition, I think it'll work as long as n is odd, right? Because I think everything should go through.
But then we don't have the sum, right?
Yeah, so you're saying we don't have the formula for this one, right?
Yeah.
Yeah, so what we do have in that case is something else. So instead what will happen, so we'll still have the same thing where, um, it's equivalent to just showing that the sum, instead of writing 1 over A, we could write A inverse, the multiplicative inverse, and then, because all the denominators are coprime to n, so like maybe I'll just say that, because all denominators coprime to n, it's equivalent to showing that, the sum over appropriate A of A inverse is congruent to 0 mod n. And now this will actually be equal to the sum over A coprime to n of A. So maybe I'll say,
Um, I think it would work
yeah, and so what's the reason?
because if x is coprime to n, then n minus x is coprime to n as well.
That's right, that's right. So the key idea is to pair up. So if x is coprime to n, this is equivalent to x minus n coprime to n. So you can pair up, A and n minus A. And so now you see why we need this n is odd condition, right? Because if n is not odd, oh, no, then it still works, right? So, hmm,
Yeah,
but
it
yeah,
still
it still works.
works.
Yeah, it still works. Okay, it's because n over 2 won't appear because it's not coprime, right? So now at least I guess that's why 2 doesn't work. The reason 2 doesn't work is because n over 2 shows up, like 1 is coprime to 2, even though it's only half.
Uh, I think um, that if n is even, then 4 divides n,
You're saying it won't work. You're saying it will,
unless 4 divides n.
and why is that? Well, so what went wrong with this argument?
Oh, no, actually.
Yeah, I think it's okay, right? If I
Yeah,
do, for example, n equals 6, I'll do 1 plus 3 plus 5, and it should be, sorry, it'll be just 1 plus 5, right? There won't be any 3, so it'll work. Really, 2 is the only problem, because with 2, the point is, okay, if n equals 2, then n over 2 is coprime to n. That's okay, some kind of weird. It's not important. But yeah. Does it make sense? Okay, so I'll go now to number 5. So number 5 is very similar. So for number 5, is just prove that if P is not 2 or 3, then in fact P squared divides R. It's an even stronger one. So by this comment, it's actually, I guess, yeah. So again, all the denominators are co-prime to P squared. So it's equivalent to showing that 1 inverse plus 2 inverse. So number 5 is equivalent to showing 1 inverse plus 2 inverse plus all the way P minus 1 inverse is congruent to 0 mod P squared. But now let's just be clear. These are inverses mod P squared. Okay, so it's a little bit different. Okay. So what can we do here?
I went about it differently and did a bit of Gaussian pairing at the start.
You're saying, okay, you did a little different. So you started from the beginning. So actually you're saying you started with you
I
kept
multiplied by 2 and added every 1 over x to 1 over p minus x.
great. Okay, so you didn't do this modular arithmetic yet. You just said, okay, this guy
No,
I
I
can.
did after that.
Okay, good. So we start actually we just do some manipulations on the fractions, and we say this thing we pair up k and p minus k, right? So we say this is 1/2 times we can
Uh,
pair up. Sorry.
it would be easier to just multiply everything by 2, I think.
Yeah, okay, good. So yeah, maybe this is x, and then 2x is equal to, or
Yeah, to avoid the cases where p is, or no,
yeah,
actually, but it would be easier this way.
yeah.
I
I
think.
think, but maybe it's roughly equivalent. But okay, but yeah. So this will be
Yeah, the
sum.
same, but
Yeah.
instead of, but we won't have to divide p by 2, p minus 1 by 2 here. The
I see. Okay.
summation.
Okay. Yeah. So let's do it. Let's do it this way. So we have this. Um. Okay. So we are just doing some pairing. And now it becomes very nice actually because yeah. So what do we end up with inside of the sum? Um, it becomes p over k times p minus k, and this is 2x. Um, so yeah, and so this is very nice because actually the p is kind of we get actually the previous problem became free now, right? We see this factor of p, right? Because this denominator is all these are all co-prime to p, right? So or maybe even, yeah. So these numbers, these are all co-prime to p, the denominator. So they won't do anything for us. So now we can say x is 2x is p times sum k between 1 and p minus 1 of 1 over k times p minus k. And so yeah, and maybe let's write it as pk minus k squared. And now, yeah, so we want to show what? We want to show that the numerator is divisible by p. And so this will be equivalent to, so this is equivalent, as we remarked before, equivalent to showing that, uh, well, so first of all, okay, let's maybe sort of, first of all, it's just enough to look at this guy and show that this has numerator uh, divisible by p, right? Because we already have one factor of p. And then we want to just show that Actually, that's equivalent to saying that p times sum from of pk minus k squared inverse is congruent to 0 mod p. Does that make sense? And that's actually much easier, right? Because okay, well now we can drop the pk. It's not important anymore, and this becomes minus what becomes 1 squared inverse plus 2 square sorry. Well, okay, maybe I'll just skip. The point is what the inverse is just they permute everything. So this becomes 1 squared plus 2 squared plus k squared, plus p minus 1 squared. I want to show this as 0 mod p. And this is why maybe you'll see now why you need p is 3, because I mean there's a formula for this. This is okay, up to the minus. This is does anyone know the formula for the sum of the squares? Maybe it's
Yeah.
yeah. Can someone remember? I forgot what it is. Maybe it's p times I have to do p minus 1 times p times 2.
It would be p minus 1 times p times 2p minus 1.
2p minus 1 over 6, right?
Yes.
Good. So now we want to say that this is divisible by p, and the point is it's true as long as 6 has no common factor with p. So this is true assuming 6 and p have no common factor. And so that's why you need to throw out p equals 3. Okay, so does that make sense for everyone? Okay, so let's go to what was the next one? Next problem was it number 8? I think.
8.
Yeah, so let's look at number 8. So number 8, so prove that for every positive integer n, there exist pairwise relatively prime integers k0 through kn, all greater than 1, such that if I look at their product k0, k1 all the way to n, I don't know why I wrote k0. Maybe I should start with k1, because you want to say there are n of them. Okay, and then you subtract 1 from their product. So this quantity is the product of 2 consecutive integers. Okay, so you want to show for every n, you can find n pairwise relatively prime integers, k1 through kn, such that if you take their product and subtract 1, you'll get something that is the product of 2 consecutive integers. So like k, something like d times d plus 1. So we want to solve, basically we want to solve k1, kn minus, k1 dot 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 kn minus 1 is equal to, say, like m times m plus 1. Okay. Yeah. So any ideas how we can solve this?
Yeah, we can think of it as uh, finding a number such that m times m plus 1 is equivalent to minus 1, is congruent to minus 1 mod n or more primes.
Great. Yes, this is the first key observation, right? That you need is you can sort of flip the problem around. Instead of finding k, you find m, right? And it's what you have to do, you have to find m such that m times m plus 1 is congruent to minus 1 mod p for at least n different primes p. Okay. Does that make sense? Then you take m times m plus 1 and then you add 1 to that, and then you take, you somehow split that number into many different factors. Does it make sense? This is sort of a very important observation. Um, and then what? So now what do we do next?
Um, we can just start by finding a way to find different primes such that there exists a number um, such that m times m plus 1 is equivalent to minus 1 would be.
Good, yeah. So
We can
yeah,
just do this by choosing an and then the factors of m times m plus 1 uh, all plus 1 would satisfy this.
good. So yeah, first we need to show, so maybe this is lemma 1. There exists at least n primes p such that m times m plus 1 congruent to minus 1 mod p has a solution. Okay. Right. So before solving them simultaneously, we need to solve them individually, right? So okay, what do I do? Maybe I will erase these. So now you're saying, Karam, I just take some arbitrary m, right? So is this the idea? So the idea is take an m, but yeah, maybe you can explain your idea again. So I have to take an m, but uh, yeah.
Um, so we can just choose any arbitrary at first, and
Uh-huh.
then start picking the primes. Um, like first we just try say 2.
Okay.
So we have 2 times 2 plus 1, all plus 1, so 7.
Mhm.
Then we can pick the asset of primes we have, in this case 7, and multiply the multiple primes we have by their multiple plus 1, and then add 1. This should be, now this should contain new prime numbers.
Great. Okay, so maybe we do this inductively, right? So, yeah, right, so I guess you're saying, yeah, so the idea is to use, maybe we say we do this by induction. So, so first P1 is maybe 7 in this way. Okay, and then we say, given P1 through maybe Pn minus 1, you can take, maybe we should be a little bit, yeah, okay, so maybe given P1 through Pn minus 1, and I can maybe consider a prime factor of, I say capital N times n plus 1 plus 1, where n is the product of all of them, P1 times P2 times Pn minus 1. Okay, prime factor, yeah. Okay, maybe I can write this a little bit more clearly. Let's just consider a prime factor of, we take their product, and then we take their product plus 1, plus 1. So we take P as a divisor of this. And then the point is that P is not equal to P1, P2. I mean, it must be different from all the previous ones, right? Does that make sense? Because yeah, P cannot divide P1 or P2 or P all the way to Pn minus 1. So P is now is a new prime, right? So yeah, so does that make sense? So the point is, there are infinitely many primes you can construct in this way, where this congruence has a solution. Okay. Sorry, my iPad is, sorry. Yeah, sorry about that. But yeah, okay. This was the argument that you can construct n, in fact, infinitely many primes, where this congruence m times m plus 1 is congruent to minus 1. Mod p has a solution. Okay. So does the argument make sense for constructing infinitely many such primes? Abdullah Karam, does it make sense?
Yeah.
Could you read the last part?
So this part here. So do you understand what we're doing? We're trying to construct, maybe yeah, what we can say like this. We're trying to construct an infinite sequence, which we're trying to construct an infinite sequence P1, P2, and so on of primes, where each one of them there's a solution to this equation, right? And the way we do it, okay, we just start with P1 is maybe 7 because then there's a solution. And then the idea is once I have P1 through Pn minus 1, how do I construct the next one? What I do is I consider this guy. So I take n times n plus 1 where I plug in this. And the point is, what is the key idea? The key idea is this means P does not divide P1 or P2 or any of these. Okay, because because P divides a multiple of something time plus 1, it cannot multiply. It cannot divide any of these. So that means if I say Pn is P. It's a new prime. Does it make sense what I'm saying?
Yeah.
Okay.
B is a new prime.
Yeah. And so now I'll get an infinite sequence, right? And they're all different. Okay, so now we still need to do one thing, right? We're not done. Yeah, so we just constructed an infinite sequence of primes where each one you can solve this equation. But what did we need? We needed one m so that it solves m times m plus 1 is congruent to -1 modulo at the same time for n different primes. So what do we do then? Right, so does it make sense what we're not quite done yet.
We just use Chinese remainder theorem.
Right, so the idea is now, okay, so by construction, there is m1 all the way to mn, such that m1 times m1 plus 1 is congruent to -1 mod p1, m2 times m2 plus 1 is congruent to -1 mod p2, and all the way mn times mn plus 1 is congruent to -1 mod pn. Okay, so what do we say? We say let m be such that m is congruent to m1 mod p1, m is congruent to m2 mod p2, and so on until m is congruent to mn mod pn. Okay, then m times m plus 1 is congruent to -1 mod p1 p mod mod, let's say mod pk for all k. Okay, and then we are done, right? It's any questions about this one? Okay, good. So so now I think now we have number 19, right? So 19 is the one I promised I would explain how to solve. So let's recall problem 19. So problem 19 is maybe I forgot how to do this. Yes, show that there are infinitely many positive integers n such that 2 to the n ends in n. So it's like the decimal representations is like many digits and then n, right? So does the question make sense? Uh, yeah, does the question make sense?
Yes.
Okay, good. So what I'll say is, if you want to show there are infinitely many things with a property, maybe it's first good to show that there's one. So first, can you find one such? And that's our first goal. So any ideas on how to find the one n with this property? So actually, if you think about it for a while, you'll realize it's not so easy. I mean, if you try all the one-digit numbers, 2 to the 1 is 2, 2 to the squared is 4, 2 cubed is 8, 2 to the 4 is 16, which ends in 6, 2 to the 5 is 32, which ends in 2 and not 5. 2 to the 6 is 64, which is still wrong. 2 to the 7 is 128, so that still doesn't work. 2 to the 9, 8 is 256, and 2 to the 9 is 512. So actually, all of the one-digit numbers fail. 2 to the n does not end at n. So any ideas what to do from here? There's no easy solution, is all I'm going to say. So I'm asking, is there a two-digit? Right. So maybe I'll say if there were such a number, so we want 2 to the power, so yeah, we want some number n. N is like a and then b or something, so 2 digits. 2 to the n. We want to say it ends in n, right? So we want to say 2 to the n is congruent to n modulo 100, right? So this is what we're looking for. So n is a two-digit number, so that 2 to the n is congruent to n mod 100. Okay. So any ideas how what to do? Or maybe even just observations. Like if there was such an n, maybe what property would it have?
It has to be even.
Right, so it has to be even because well it's a power of 2 mod 100, so it has to be even. Um I guess we need to observe. So yeah, n is not 0, therefore 2 to the n is even, therefore n even. Okay.
There also has to be a cycle that repeats in the powers.
There has to be a cycle that repeats. I mean, so this, if you look at powers of 2, right? These will always repeat modulo anything. Modulo like any number, maybe mod m, let's say. But maybe I'll make some comments. So how does it repeat, right? So it kind of depends on m, right? So let's maybe have an aside here. Yeah, so I'll take this to a new page. If you consider the powers of 2, so let's fix a modulus m, and we consider the powers of 2. So 2 to the 0, 2 to the 1, 2 squared, 2 cubed, and so on. And you consider this sequence modulo m. So what does it look like? So first of all, we should consider maybe modulo prime powers. So let's say modulo p to the k. And the reason I say consider a prime power instead of a general m is because of Chinese remainder theorem. It's okay to split up into prime powers. Okay. So first of all, okay, if p is 2, so if I did 2 to the 0, 2 to the 1, 2 squared, and so on, this sequence mod 2 to the k for some k, what does the sequence look like? Like how does it repeat?
It doesn't.
Sorry?
It doesn't.
Well, I mean, I mean, it doesn't repeat completely, but I mean, eventually it becomes constant, right? Like it'll eventually become like 0, which is okay. So it'll eventually just repeat 0 over and over again, right? Yeah. But now I guess my point is if I consider any other prime, mod p to the k, now it will like really repeat from the beginning, right? And yeah, so there will be some 2 to the d, which is congruent to 2 to the 0, and then it will repeat. Okay. And why is this true? Well, this is true because of this theorem, like 2 to the um, phi, right? So what is it? In this case, so maybe what is the point? So phi of p to the k, this totient function is p times p to the k minus is what? Is phi of p to the k is p minus 1 times p to the k minus 1. So if I take 2 to the p minus 1 times p to the k minus 1, this will be 1 mod p to the k. So it means at least if I go um, if I go in the sequence by this quantity, it repeats, and it may actually repeat sooner. We don't know, but at least if you go by this amount, it repeats. Yeah. So I guess what I'm saying is certainly it's true that d divides is some divisor of this. Yeah. Does that make sense? So
Yeah.
yeah. So here I guess what we're saying is, so what's the important thing here? We can consider like this. So we can take this equation and we can split into 2 to the n is congruent to n mod 4, and 2 to the n is congruent to n mod 25. And here, the powers of 2 will repeat at least what? So at least every 20. So 2 to the power of 20 is congruent to 2 to the power of 0 mod 25. Okay. Yeah, okay, so that's is that. Okay, yeah, so any other observations? So we observed that n is even. Is there anything else we can observe?
And it's not a multiple of 10.
N is not a multiple of 10. How do you know that?
Um, because any power of 2 cannot end with 0.
Ah, right. Okay, yeah. So n is not a multiple of 10. So 10 does not divide n because 2 to the n does not end in 0. Okay, good. It's a good observation. So there's another observation here which is similar to this, right? So we concluded that n is even. I claim you can do even better than that.
4 divides
Yeah, so actually 4 divides n, right? Because of the same reason, really, right? So yeah, we can say 4 divides n because, well, what's the point? I guess, yeah, n is not 0 and n is not 1. Okay, so as soon as n is not 0 and n is not 1, it tells us that 2 to the n is 0 mod 4, or maybe we can just say 4 divides 2 to the n. Okay, which means that 4 divides n. Okay, so yeah, so n is a multiple of 4. So that actually, yeah, we kind of this, this part of the thing actually comes for free. Does that make sense? So once n is divisible by 4, we don't need to worry about this. And so we only need to worry about this one. Does that make sense? So yeah, so we can sort of, okay, let me sort of reorganize all the information. Yeah, so we can all write it here. We are looking for yeah, so what property does n need to have? So n is a 2-digit number. Okay. And we need 4 divides n. And now we just need 2 to the n is congruent to n mod 25. Okay. So we dropped we dropped one of the conditions, right? I guess we started with this condition and it split into these 2 conditions. And now we're just dropping this first one because it comes for free if we say 4 divides n. Now, yeah, so yeah, so any idea what to do for this one? Maybe is there a simpler problem that we could solve first? So we want 2 to the n is congruent to n mod 25, but is there something easier we could go for? Does it make sense what I'm asking? I'm asking, okay, maybe it's hard to find. Maybe this is hard to solve. Is there something easier?
Yeah, we can just use mod 5.
That's right, yeah. So the first step will be actually we try to find. So instead, let's just try to find 2 to the n is congruent to n mod 5. Let's keep these conditions. So let's keep that n is 2 digits and 4 divides n and try to find n so that 2 to the n is congruent to n mod 5. And this one actually there's not a unique, but a more or less almost unique solution. Not quite unique, but as in you can find maybe I'll say this, you can find all n so that this is true. So I'll give you some time to think about this. Right? So what we're looking for, n is a 2-digit number that's divisible by 4, and 2 to the n is congruent to n modulo 5. I think you can find all the n with this property. So think about this sequence, 2 to the 0 to the 1. Think about the powers of 2 mod 5. What do they look like?
Yeah, so the powers of 2 and 5 repeat in cycles of 4 elements.
That's right. So they'll repeat every 4, right? So
But n will repeat every 5,
that's right.
so we can find n with any mod. Uh, uh, so we can find n in any register class mod 5 that satisfies this.
Yeah, so you're saying, great. So this is a good observation. You're saying since the yeah, so you're saying n mod 5. Sorry, I would like to still continue using blue. So maybe I'll use red. So your observation is n mod 5 repeats every 5, but 2 to the n mod 4 repeats every 4. So you can actually make it so n and 2 to the n are equal to whatever you want, right? The key point is 4 and 5 are coprime. But remember, there's still these 2 other conditions, right? So we're actually saying, we're insisting 4 has to divide n. So actually this part, yes, it's true, 2 to the n repeats every 4, but this actually fixes what the value of 2 to the n is. Do you see? Do you see what I'm saying?
I think. Mhm.
Like remember, I'm looking for n that satisfy the property n is 2 digits, n is divisible by 4, and this, right? Since n is divisible by 4, 2 to the n is actually fixed. It's maybe I'll start a new page. So yeah, so what am I saying? I'm saying
Oh,
yes.
okay. Now I get 2 to the n is equivalent to 1, 5.
That's right, that's right. Yeah. So I'm saying because yeah, so let's maybe it's continue in blue or something. Because um because um 4 divides n, 2 to the n is congruent to 1 mod 5, right? So it actually tells you that n is congruent to 1 mod 5. So if you just wanted to solve, you know, uh, n is 2 digits and n is divisible by 4 and 2 to the n is congruent to n mod 5, the only conditions you have is that is you really all you end up with is 3 things. N is 2 digits, 4 divides n, and n is 1 mod 5. And so there are not very many numbers that satisfy this, right? Because I think we can just say all of them. So um, the smallest one will be, what, so 4, 12, 16. 16 will be the smallest one. So 4, yeah, so 16. And then from there, it'll just be increasing by 20. So 16, 36, 56, 76, and 96. These are the only ones that should work, right? Basically 16 mod, yeah, maybe it's basically 16 mod 20 is the, by Chinese remainder theorem, this is the same as 16 mod 20. So I'll say, um, good. So now what do we do? So we know that these 5 numbers, like, as long as you're 16 mod 20, or which is you satisfy these 2 modular congruences, it's going to be true that 2 to the n is equal to n mod 5. So for which of these is it also going to be true that 2 to the n is congruent to n mod 25? That's the question. Right, so yeah, yeah, so far we have this. So I guess, yeah, here's my point. Claim. What's the claim? So this information, I say 4 divides n and n is congruent to 1 mod 5. Or in other words, n is 16 mod 20. I claim this determines 2 to the n mod 25. Okay.
Yeah, because Euler's tangent function for 5 squared is 20.
That's right. If I take the tangent, I get 20 here, right? So this was the this observation. Maybe we had it before, or maybe okay, maybe I lost it. Yeah, there was some observation that the powers of 2 mod 25 will repeat every 20, right? So yeah, this will determine 2 to the n. And yeah, so what will it be? Maybe we can just calculate, right? So mod 25, right? So it'll be maybe we can calculate it. Um, can we calculate it? So 2 to the 16 mod 25, right? So how do we calculate that? Yeah, so the point is it's 2 to the 4 yeah, it's 2 to the 4 to the 4, and then this is equal to 16 to the 4. And what was the point about 16? 16 was already 1 mod 5, so we can write this is equal to 1 plus 3 times 5 to the power of 4. Okay. But now, since we're working modulo 25, this is equal to 1 plus, I'm going to use, this is binomial theorem, right? So binomial theorem. So it'll be 1 plus 4 choose 1 times 3 times 5. And the higher terms don't matter. Mod 25. Does it make sense? Any of the following terms will go away. So this will be 1 plus 4 times 3 times 5, which is um, I made a mistake. No, this is not right. So what is the mistake I've made? Oh no, maybe it's not a mistake. Yeah, it's not a mistake. Yeah, so this is 61, which is um which is 11 mod 25, right? No, sorry, this is not 11. This is a 1 mod. No, this is yeah, this is 11 mod 25. Okay. So, right. Yeah. So what is the point of all of this? Now we need to look at all of these 5 numbers and we need to decide which one is 11 mod 25. Does it make sense what I'm? Yeah. Right. Does it make sense what I'm saying? Yeah. So let me repeat. So we calculated 2 to the power of 16 is 11 mod 25. And since the powers of 2 repeat every 20 mod 25, all of these numbers, when you take 2 to that power, will be 11 mod 25. So we just need to decide which of these numbers is 11 mod 25. Does it make sense what I'm saying?
Yeah.
And moreover, you should know that actually exactly one of them is going to be 11 mod 25. Because they're already 1 mod 5, right? They're already 1 mod 5, and then you jump by 20. So yeah, so let me sort of right, so let me explain this. So now we want to know yeah, so we did this calculation and then yeah, So we want, you'll write here, we want which of 16, 36, 56, 76, 96 is 11 mod 25. And the point is, they're already 1 mod 5, so exactly one of them will, right? So it'll be like, okay, it's like 16 plus 20 times k is congruent to 11 mod 25. So yeah, the point is these already match mod 5, and this thing is a multiple of 5, but not 25. So one of them should work. Does it make sense? But I'm not explaining it very well, but I hope there should be a unique, k that works. I mean, certainly by inspection, like, okay, this is 16, and then this one is 11, right? So okay, this one is 6, and this one is 1, and then this one is 21, right? Okay, so it's this one. Does it make sense?
Yeah.
Yeah. Okay. Yeah, maybe it'll be more clear as we do some, maybe. Okay. Okay, good. Yeah. Okay, so what the point of all this is that the number 36 works. Okay, 36 will work. Yeah, I hope the explanation is clear. So the point of all of this is that 36 works. Okay. And when you do this, what you get is 2 to the power of 36 is congruent to 0 mod 4, and it's congruent to 11 mod 25. And it's also true that 36 is 0 mod 4, and 36 is 11 mod 25. Okay. So that's okay. So that's one number that works. Okay. Yeah. So what should we do next? So remember that the problem was to find what, infinitely many n, so that 2 to the n ends in n. We found 1. And moreover, we found that among all two-digit numbers, there's a unique one. So now what should we do next? So I think the next thing we should do is just find another one. What is the next number where this is true? So yeah, so what we should do, we should try 3-digit numbers, I guess, next. So let's try. Yeah, so for the second one, let's try 3-digit numbers. And the idea is, okay, now we take n is 3 digits. And what we want now, we want 2 to the n is congruent to n modulo 1000. Okay. But again, in light of the Chinese numerical theorem, we should think of this as 2 to the n is congruent to n mod 8, and 2 to the n is congruent to n mod 125. And so, yeah. So any initial observations? So I think before in the previous one, right? The very first thing we observed is that n was even. Okay, maybe the order is kind of weird. But yeah, the very first thing we had observed was that n was even. And then moreover, that was a multiple of 4. So in this case, I think it should be that n is a multiple of 8. Does that make sense? At
Yes.
least, yeah, so provided as, maybe n is at least maybe 3, but that's reasonable. So n is a multiple of 8. Okay. And now, so now what we can do, we can actually just, okay, we can say we take out this condition and we just instead say n is a multiple of 8. Then we can sort of forget about that condition. Okay, so now what do we have? We have n is 3 digits, n is a multiple of 8, and we have this guy. Okay. But now, I'll say, well, the idea is, most of this is actually solved for us, right? So, yeah, so what's the idea? So the idea is, maybe this is a little bit hard. So let's replace it with, so yeah, so let's instead try to just do n is 3 digits, n is a multiple of 8, and now 2 to the n is congruent to n mod 25. Okay. And, I claim, well, okay, what is the point? You've actually already solved this, more or less, right? Do you guys see what I'm saying? Like what you had solved before was what to do if 4 divides n and 2 to the n is congruent to n mod 25, right? So that was, I mean, this in this previous one, what was the whole point of this thing? If n is the point is if n is divisible by 4 and n is and 2 to the n is congruent to n mod 25, the conclusion is that uh, uh, n is 11 mod 25. Does that make sense? Like this whole calculation, what it showed is if I assume these two, then I get that n is 11 mod 25. And so the same thing applies here, right? Because you're saying 8 divides n, which also means 4 divides n, and 2 to the n is congruent to n mod 25. So should actually these two together should give us by by the previous calculation, this is the same as n is congruent to 11 mod 25. Does that make sense, what I'm saying?
Yeah.
Yeah, so this, I mean, there's nothing very subtle going on here. I mean, there's something like, okay, but it's true, right? So like this, what it means is these two conditions, these last two at least, it's equivalent to n is a, b, c, 8 divides n, and n is 11 mod 25. It's equivalent, right? So now, yeah, so now maybe we can figure out maybe what this number is. And yeah, so what is this number going to be? If it's 8 divides n and n is 11 mod 25. So before we said what? If n is 11 mod 25 and 4 divides n, it was 36. So 36 won't work. Right, so unfortunately, 36 won't work because it's not divisible by 8, but we should add 100, right? So then we should get 136 mod 200. Did you guys see how I got that? So I knew 36 would be basically 4 divisible by 4, and n is 11 mod 25. So then I needed to get divisible by 8. I just added 100. Does that make sense? And so now I have 136 mod 200.
Yeah.
Yeah. Okay, good. So we have 136 mod 200. So that's yeah. So that's to get these conditions. But of course, what we were after is slightly stronger. We are after even 2 to the n is congruent to add mod 125. So we need to add this one, right? But again, what we'll see is there's a unique way to do this, right? So what's the point? Yeah. So what's the point here? The point is, what is phi of 125? This will be 5. This will be 4 times 5 squared, which is 100. So what I'm saying is these two will actually determine n 2 to the n mod 125, so it'll determine n mod 125, right? So what I'm saying is just like before, so yeah, so maybe I need some more space. Uh, so as before, we'll have now n should be congruent to 2 to the 136 mod 125. That should be what we get, right? Maybe I can be a little bit more clear. So okay, we know yeah, what am I saying? So I'm saying okay, so we have 8 divides n, and we have n is 11 mod 25. So these two things will guarantee that 2 to the n is divisible by 8, and 2 to the n is 11 mod 25. But what I'm saying is a little bit stronger. So I'm saying that pick maybe n0 such that, yeah, so n0, let's say in 1 to 1 0 1 to 124, such that no, maybe it'll be up to 200. Shit, what am I saying? I'm saying pick n0 in 0 to all the way to 199, such that n0 is congruent to 0, mod 8, and n0 is congruent to 11 mod 25. And now I'm saying, what do we want? We want, so now it's guaranteed that, it's guaranteed that, sorry, I'm a little confused here. Yes, so it's guaranteed that 2 to the n0 then is congruent to 0, is congruent to uh, 0 mod 8, and 2 to the n0 is congruent to 11 mod 25. But this is also true, right? So this is not only true for n0, but it's also true for n0, n0 plus 200, all the way to n0 plus 800, right? It's true for these 5 as well. Does it, right? And then what I'm saying is, um, uh, yeah, okay, maybe I need to be a little bit clearer. So it's not quite that. What I'm saying, it's further true that 2 to the n0, 2 to the n0, uh, mod 125. Right, so these are all equal mod 125. Sorry, I'm doing a very bad job of explaining what I'm saying here. So, right, so n0 solved this congruence, which means that this is true, right? So both n and 2 to the n are equal mod 8 and mod 25. Okay. But then I'm saying further it's true that because because phi of 125 is just 100, right? It's true that each of these guys also satisfies, I mean, it satisfies this as well, and they're all equal mod 125. Hmm. Okay. Yeah, okay, maybe people are confused. Do people understand what I'm doing here?
Um, I think, yeah, I think you've given us enough insight into the problem. I think
Okay.
I want to try it again
Okay.
by
Okay.
myself.
Okay. Yeah. Okay. Maybe that's, yeah. So maybe it's a good point for me to stop. So, yeah. Okay. Yeah. So sorry, I didn't do a very good job explaining the problem, but hopefully you have some ideas. Yeah. So here's what I'll do. Right now I can't figure out a good way to explain this. But the ideas are all there, so maybe you can think about it on your own. And then what I'll do is this weekend I'll write a solution which is easier to understand, and I'll send it to you guys. Um, yeah, does that sound good?
Yes.
Okay, yeah. Yeah. Okay. So is there anything else you wanted to discuss from this number theory problems? Maybe if there's something you're stuck on, I can give some kind of hint. Okay. Yeah. So in that case, yeah. So I guess we can call it a day. Um, Abdullah, you mentioned you wanted to go over this the combinatorics problem from last time. Do you still want to? I don't know, do you have energy to, or do you have time?
Maybe I'll try it again. Uh, I wanna
Okay.
try to solve it myself.
Okay. Okay, that sounds good. Um, yeah, but so if you do solve it, please write a solution. I think it's a good one to write a solution for because you'll realize whether you solved it or not. Uh, okay, so I guess that's it for today. I'll